Astonishing detail emerges in latest solar flare photos. But here's where it gets controversial. These images could force us to rethink how solar storms actually build and erupt. The sun constantly unleashes powerful bursts of energy known as solar flares, which are sudden explosions of light and radiation. Right before these flares appear, gigantic loops of superheated plasma, called coronal loops, arch gracefully above the solar surface, tracing the sun's magnetic field lines. Now, thanks to the Daniel K. Inouye Solar Telescope, the world's most powerful ground-based solar observatory, astronomers have captured razor-sharp views of both a flare and its coronal loops in ways we've never seen before. Captured on August the 8th, 2024, during the fading phase of a strong X1.3 class flare. These high-resolution images at the hydrogen alpha wavelength, 656.28 nanometers, reveal loops as narrow as 13 miles, 21 kilometers, across and averaging just 30 miles, 48 kilometers, in width. To put that in perspective, these loops are only a few times wider than a city, making them the tiniest solar structures ever directly imaged. Before this, we could only guess at how fine these magnetic strands might be. These are the smallest coronal loops ever imaged on the sun, says Cole Tambouri, lead author of the new study and PhD candidate at the University of Colorado Boulder. Catching an X-class flare under perfect conditions was pure luck. And now we're seeing the sun at the scales it actually works on. The movie sequence from the Inouye telescope, sped up 100 times, shows bright ribbons of flare energy weaving between darker, thread-like loops in a scene spanning 4 Earth diameters. Observers can watch plasma swirl along these loops, then snap and reconnect, a process known as magnetic reconnection that powers the flare itself. Here's the part most people miss. These loops might not just be decorative arcs. They could be the fundamental building blocks of solar flares. If each tiny loop acts like a single brick in a larger storm, resolving individual strands for the first time opens the door to entirely new flare models and more accurate space weather forecasts. That's crucial, because intense solar flares and the charged particles they fling toward Earth can wreak havoc on satellites, power grids, and radio communications. By understanding loops at their true sizes, down to the tens of kilometers scale, we gain insight into where and how reconnection happens, improving our ability to predict when a solar storm will strike. The research team, spanning the National Solar Observatory, University of Colorado Boulder, LASP, and Ceres, published their findings in a peer-reviewed paper in the Astrophysical Journal Letters on August 25, 2025. They highlight that the Inouye telescope's visible broadband imager can discern details as small as 24 kilometers, over 2.5 times sharper than any previous solar telescope. Knowing a telescope can theoretically do something is one thing, adds co-author Maria Kazachenko. Actually watching it perform at that limit is exhilarating. We aimed to study chromospheric dynamics, but instead stumbled upon these ultra-fine coronal structures. Controversy comment hooks. Some in the solar physics community argue that resolving finer loops won't fundamentally alter flare theory, that magnetic reconnection occurs in much larger regions anyway. Do you think these tiny loops will rewrite our understanding of solar eruptions, or are they just a beautiful sideshow? Share your thoughts below and let the debate begin.